right? This is a slide we ended off with. Sorry, I got cut off short. I wasn't paying attention to the time and I lost time. But again, here's our bonds. We have a nonpolar sharing equally, polar not so much sharing equally, positive end, negative end, and then we have an ionic where you have a positive cation and a negative anion. Okay, so how can you figure that out? Well, it's easy to figure out an ionic bond because it's a metal and a nonmetal. Okay, the farther they are from each other in the periodic table, the more likely it's ionic. But how do you tell the difference between a nonpolar and a polar? Because they're sharing the electrons. Okay, there's something called electronegativity, and there'll be a chart in here that you can run off. But what it does is electronegativity is how much do they really want those electrons. Okay, the higher the number, the more they want electrons. Okay, and you can see every element except for the noble gases, they're not even listed here, has an electronegativity. The noble gases don't have one because they don't want electrons. But the metals have low numbers and the nonmetals have high numbers. Okay, so they get, when you go left to right across a period, they're going to get higher. And when you go from bottom to top, they're lower here and they get higher up here. Because again, these ones are farther away from the nucleus, so they don't have as much control over them. Okay, but anyway, electronegativities is they've been assigned a number, and what you do is you can use them to figure out your type of bond. And again, after this lecture, you'll see there's a chart you can print off to see it. Okay, all right. So a polar bond, what you have to do is you look up their electronegativities and you subtract the difference between them. Okay, if you take your two elements, subtract the higher number from the lower number. Okay, if the difference is 0 to 0.3, it's a nonpolar covalent. They're sharing electrons, sharing them equally. If it's between 0.3 to 1.7, that's a covalent bond, but it's a polar covalent bond. They're sharing their electrons, but they're not sharing them equally. And if the difference is higher than 1.7 or higher, then it's an ionic bond. Okay, here they show some differences. Electronegativity difference between hydrogen and fluorine is 1.9. That should be an electric bond. That should be an ionic bond, and most of the time it is. But the thing with hydrogen won't give up its electron. So if you have hydrogen, you're going to form a covalent bond. In most cases, they're polar covalent. Here's a better one: hydrogen and chlorine. The difference is 0.9. Okay, so again, you're going to end up with a positive end and a negative end. They're sharing their electrons. They're forming a molecule, but they're not sharing them equally. If you do hydrogen and bromine, they're a little less with the poles because they're a little less difference. And hydrogen and iodine, the difference is only 0.4. So again, but all you have to do to figure out what type of bond you have is take the electronegativity. If the difference is 0 to 0.3, it's a nonpolar. If the difference is 0.3 to 1.7, it's a polar covalent. And then if it's above 1.7, it's ionic. So that's a simple way. The greater the negative electronegativity, the more polar the bond is, actually the more ionic the bond is, okay? So you can draw what they call dipoles, okay? And what it does is it goes from the positive to the negative. And you can tell which one it is because the one that has the lower electronegativity, okay? So fluorine is actually the highest of all elements. It has electronegativity of 4, and that's the highest it can possibly be. But you can draw it out like this. And this will show you in a covalent bond, a polar covalent bond, where the positive end is and where the negative end is. Okay? So electrons tend to spend more time around the more electronegative atom, this one, because it's got a stronger pull of its nucleus, so it pulls the electrons closer to it. So this is why you get a negative end over here and a positive end over here. And this is how you can draw it. Okay? And again, if you actually do the numbers here, this should be an ionic bond, but hydrogen will not give up its electron. It's like a mother with a single child. Smother that baby, keep him close, so he won't give it up. That's a weird thing about hydrogen. You remember, hydrogen is really a weird element. It does its own thing. Okay, again, but this is how you draw it. This is the positive end, this is the negative end. And this is kind of easy to remember because you got a little P right here, a little positive there. Okay, so is a compound ionic or covalent? Well, if it's a metal and a nonmetal, it's an ionic one, you guys. If it's two nonmetals, it's going to be covalent. But again, you can also use electronegativity differences. There are exceptions. Okay, sometimes it doesn't take account oxidation numbers of a metal. Sometimes there are always exceptions to the rules, but we're going to stick with the regular rules. Okay, like I said, we're not going to even deal with transition because they got some funky things going on there. We're not going to deal with that. Okay, we're just going to go with the standards. Okay, You can use the electronegativity difference. That's an easy way to tell. And that really helps with the nonpolar and the polar. Okay? So when you look at the difference between the two types of bonds, the ionic versus the covalent, ionic is a stronger bond. So because it's a stronger bond, it has a higher melting point and boiling point. When you do a covalent bond, if you take a covalent compound, it's much easier to melt. Like you can melt it if you put it on a Bunsen burner in probably 30 seconds. If you do a covalent bond, or an ionic bond, excuse me, you could cook it all day and it won't melt. So ionic bonds are stronger, much stronger, okay? So when you're talking about the number of bonds for nonmetals, remember they need 8. So they're going to form 4 bonds, okay? Now the 4 bonds can be in a different way. If you look here, we have hydrogen and fluorine. Okay, this line, and I wish they would have done dots, but a line represents 2 dots. This is a bond, and a bond is always two electrons. So if you look here, fluorine has 2, 4, 6, 8, and hydrogen only needs 2. Okay, and that was on that video. I hope you got that. But hydrogen only needs 2 because it's a small element and only has room for 2. Everybody else needs 8 but hydrogen. Okay, so by doing it this way, they got 2, that has 8. When you do water, oxygen has 6. So it has 4 here, and then it has 1 here and 1 here, and it shares with hydrogen. These are called Lewis structures, and what they do is represent where the electrons are. I have a little video, I'll show you how to do those. But anyway, the thing to remember is nonmetals need 8, except for hydrogen. Hydrogen only needs 2. And they will situate themselves so that they have 8. Okay? To get the octet, like a noble gas, the simplest covalent molecules, again, are 2 nonmetals. Sorry, my eye's itching right now. The number of bonds needed will be the same as the electrons needed to complete the octet. Okay, so like nitrogen has 5. It's in the 5th group. It has 5, so it's going to need to form 3 more bonds, and that's how it gets at 8. Carbon is in group 4, needs to form 4 bonds. Okay, oxygen's in group 6, has 6, and only needs 2 more, so it forms 2 more bonds. Okay, so these are called Lewis structures, and we're going to do some more complex than these, but the gist of it is they've got to have 8 electrons around them. When everybody has 8, again, except for hydrogen, which only needs 2, then everybody's happy, and you've got a compound, and you've got a stable compound. Okay, if they don't have 8, they're going to keep reacting until they get 8, and that's how it rolls. Okay, I think we're going to quit there because I want to do some more with electronegativity. So okay, we'll finish up this chapter. I think we'll do it on the next set of slides. Okay.